When making life-saving medicine in a modern pharmaceutical facility, perfectly still water is actually a surprisingly dangerous ingredient. If purified water rests for even a moment, microscopic bacteria latch onto the surfaces and create permanent, slimy layers called biofilms. If the water stops moving for even a single second, the living water dies and contamination spreads. The water in a pharmaceutical plant must stay in constant, unbroken motion to stay sterile. So before a factory can produce a single safe pill or vaccine, engineers have to solve one enormous problem: how to keep tons of water in constant, reliable motion. Modern medicine factories use thousands of gallons of water every day. That water constantly loops through miles of intricate stainless steel piping. If you tried to turn the system off to scrub all those pipes by hand, you'd expose the inside directly to the outside air, inviting the exact microscopic contamination you are trying to prevent. The answer to this problem comes from an insight Daniel Bernoulli had back in 1738. He wrote down a rule about how fluids behave when they move through a space. Using his math, modern engineers can design pipes that actually clean themselves from the inside out, 24 hours a day, without anyone ever lifting a brush. To understand his math, imagine a busy 4-lane highway. Suddenly, construction forces those 4 lanes to merge down into just 2. If the same total number of cars needs to get through that bottleneck every minute, the cars squeezed into those 2 lanes have to hit the gas and drive much faster. This chart compares the speed of the water with the pressure it exerts against the pipe walls. Think of the water as having a limited energy budget. If the water spends more of its energy moving forward faster, it has less energy left over to push outward against the sides. So as the speed goes up, the pressure against the pipe has to go down. By changing a pipe's shape, engineers use this energy trade-off to control exactly how fast water moves and presses against the metal. This control lets us create a state where the water is constantly churning and mixing. We need the water to be chaotic as it moves to keep the system clean. If water travels in a smooth, straight line, it glides gently over the metal. That gives microscopic bacteria the perfect opportunity to grab onto the sides and start multiplying. Engineers use calculated pipe sizes to keep the speed high enough that the water never settles into that smooth, dangerous state. Instead, it stays in a constant, tumbling mess. The water's constant momentum acts like an invisible scrub brush, washing the inside of the metal so forcefully that bacteria simply cannot hold on. Sometimes physical scrubbing isn't enough, and we need to add a sanitizing gas called ozone to the water. But putting a mechanical mixer inside the pipe gives bacteria a physical surface to hide on. Pinching a pipe tight increases speed so much that pressure drops below 0, creating a vacuum. We attach a small opening exactly at that point. It acts like a straw, pulling ozone gas directly into the fast-moving water and mixing it instantly. There are no moving parts to break or trap bacteria. It's a way to mix substances using only the shape of the pipe and the laws of physics. Those same narrow points let us measure the water's speed. By reading the pressure difference between the wide part and the narrow part, we know exactly how fast the water is moving, without putting a single mechanical sensor into the flow. A mathematical rule worked out on paper nearly 300 years ago ensures we can safely mass-produce the medications and vaccines that hospitals rely on today. Did the highway metaphor make the math click for you? Let me know in the comments. Want to see how we manage the temperature of all this moving water? Tell me if you want a video on heat exchangers next. Because making sure our medicine is safe comes down to something very simple: making sure the water never, ever stops moving.